No. Hello and welcome everyone. This is the Ethereum Engineering Group meetup, and today I've got Dominik with me, who is going to tell us all about Miden. So Dominik, before you share your screen, why don't you tell us a bit about yourself so the audience knows who you are?
Yes, sure. So yeah, thanks for having me, Peter. I'm Dominik, and basically since 6 years, I would say, I'm trying to scale Ethereum, like in several projects. I started with the Raiden network in 2017, and it was a payment channel network, and that didn't work out, but we learned a lot, I would say. And I joined Consensus and worked on the bridging feature for MetaMask, also in a broader sense to scale Ethereum. And then I met Bobbin from Miden, basically. And I think this time it might work out using zero-knowledge technology that could be a game changer in Ethereum scaling. So let's see. But yeah.
It's definitely Miden and not Miden, because I know some people have asked about this. So let's see how you pronounce it. We'll listen really carefully.
It's like a Polygon Miden.
Ah, okay. Oh, yeah, sure. Okay. All right. Please share your slides and yeah.
Good. Yeah. And please also, yeah, if you have any questions, just jump right in, and we can show some code, or later we will also show some code, and just like let it be a dynamic session. And if you have questions, then just jump in. But yeah, so it's Polygon Miden, and our goal is to extend Ethereum's feature set. So basically, we try to extend Ethereum's feature set to enable novel applications and maybe use, hopefully, real-world applications that are currently not possible on the EVM. And so basically, we try to evolve Ethereum as a design space. This is how we think rollups can be. And we try to make it more scalable and safer. And we want to add privacy as features. And what we mean by that is on the scalability dimension, we want to have the ability to handle a high load over an extended time. So we don't want to be confronted with state bloat, meaning that if you would run an EVM system with very high load over an extended period of time, then the state will blow. And the same with like execution bloat. If many users at parallel want to use account-based systems, then the fees will spike and everything will blow up. So we try to change that. We try to add at the safety dimension or we try to reduce basically human errors and attack surface with account abstraction, for example, but also with different programming languages like Move, for example, that are supposed to be safer than Solidity. And we want to have, or we envision a private system, a private rollup that has private account state, but also privacy on the transaction graph. So I don't want that everyone sees how much assets I have in my account. And like we designed the following features, and then it gets more technical, but this is still our goal, basically. We have client-side proving, meaning that in our rollup, it's like that Miden users will be able to create their own zero-knowledge proof and prove their own state transition to the network. And this leads to very cheap and private computations. Basically, you can locally execute smart contracts and prove to the network that you did something correct, and the network only verifies. And this is like way cheaper because the network doesn't need to recompute, and it is also private. And we will look more in depth into how this feature works also with shared state. We will have on and off-chain data meaning that in theory, the network only tracks a commitment to my state or a hash to my state, but the network doesn't know what's actually happening in my account. And this obviously helps me to hide my account and even my transaction graph. And I will show you how. We want to have parallel transaction execution to be able to have, to handle this high load. And yeah, it's quite interesting how this works, but this helps us, I guess, to build, or helps developers to build on Miden high throughput applications, so that many people in parallel can use the same step. And we have a feature to update and recall transactions, meaning that in theory, when you send something to the wrong address, you can just recall it and consume the transaction yourself, or you can update it for free, meaning that you can change your mind, or it's especially interesting for DeFi applications when you have an order and you want to change the order afterwards and say, okay, now I offer 5 ETH for 100 Matic instead of 4 ETH for 100 Matic. And this is for free and quasi in no time. Yeah, and let me explain the architecture, how we achieve these features, and you can jump right in. But our approach basically is, and this is the cool thing about Rollups, as you know, is that you can experiment with the models, with the execution models and the state models, and you can still inherit Ethereum security. And our approach is a mixture, a hybrid between the account model that Ethereum uses, or most smart contract platform uses, the UTXO model that you get from Bitcoin, and zero knowledge proofs. And this basically leaves us with an actor-based model with concurrent off-chain state. So this is our state model. And yeah, let's dive in. So basically, we start with how a transaction works in Miden, and then we will slowly build up how state is tracked. But basically, a transaction in Miden is loosely modeled after the actor model. And the actor model is a model for distributed databases, for high performance databases, that basically has this paradigm that actors are little state machines responsible for their own state. And they have inboxes, and they can send messages to each other to change their state. So basically, actor 1 sends a message to actor 2, and these messages are produced and consumed asynchronously. And if there is a state change in actor 2, then he can produce messages to trigger state changes in other actors and send messages out. And if the other actors choose to, then they can change their state. And this already is different to how it works on Ethereum, where you have state globally tracked in a global register of accounts, and they get changed sequentially. What was their question? Okay, but like here, it's important. Actors are state machines with inboxes responsible for their own state. And in Miden, our actors are called accounts, and the accounts have a state. This is the same as in Ethereum, an interface. So all our accounts are smart contracts with functions that can be called. But still, they work like as a mental model the same way as an actor works. So they send nodes to each other, like bank nodes. These are our messages. And like a node can leave an actor and be consumed by another actor. And these are the basic or the core concepts of Miden. So accounts can hold assets and nodes can hold assets. And like in the actor model, it can be done asynchronously, that actor 1 produces a node and sends out 5 Ether in the first transaction. And in the second transaction, account 2 consumes this node and basically consumes these 5 Ether by taking the node and putting it into his wallet. And because these two transactions are distinct, we get very nice properties. And but this is our model. So there are accounts and nodes. Both entities can hold assets. Both have a state, so to say, and accounts can produce and consume nodes. And in that way, the accounts communicate to each other. And when we look back at a transaction basically is a transition function of an account from one state to another. And a transaction is always only executed against a single account. So the transaction takes an account and brings it to another state. And in doing so, it consumes 1 to n nodes or 0 to n nodes, and it produces 0 to n nodes. And that is super important. The transaction is only always executed against a single account. And this is different to Ethereum or to any account-based model, where you can think of a transaction is always like at least has 2 accounts involved. And the state of these 2 accounts are changed atomically. So if I send something to Peter in Ethereum, then there are at least my account and Peter's account involved, and it can be more complex. Whereas in Miden, it's always only 1 account. And because it's always 1 account, this account can be responsible for its own state and create a proof on its own for its own state change. And you can keep this in mind. But yeah, like this is a new concept, basically how transaction works in Miden. But when you have understood this core concept, then we can build up everything from there. So there are accounts and nodes, both can hold assets, and basically they send banknotes to each other, and a transaction is always consuming several nodes, producing several nodes, but only executed against a single account. And so, because we are a zero-knowledge rollup, every transaction has always a transaction proof. So this state change of this 1 account is being proven with the Miden VM. And so the correctness of this transaction execution is be proven and will be verified by the network. And as I said, because it's always a single account, we can parallelize this proof creation and transaction execution, basically. So every user could create its own transaction proof and send it to the network. And like this is how the network works then. So we can have these many transaction proofs parallel, and they get recursively batched into batch proofs, and that at the end gets batched into a block proof, and it is still open or spec how many blocks we batch together to Ethereum then at the end. But basically the upper part must be done by the network operator, like batching and putting the proofs together in a block. But the lower part can be done locally by the users themselves. And this is how you get parallel transaction execution, basically. So this is what I said, like when we look at a transaction from the process perspective, basically we have a prepare part, we have an execution part of the transaction and a proving part in our system. So every transaction has always a proof, and that results in this transaction proof. And there could be a network execution of this transaction. This is the first type of a transaction, and this is exactly like it is in other zero-knowledge rollups. So a user prepares a transaction, let's say in MetaMask or so he signs the transaction and fills in the data, and then execution and the proof is done by the sequencer and the prover in the network, in other networks. And in Miden, basically, there is the second option that preparation, execution, and proof can be done by the user, and then only the proof is being sent to the operator, who verifies it and might not even know what happened. When we compare these two modes, basically, then you can say when you have shared state, and in a second I will explain in more detail what it is, but when you think of a smart contract that needs to be accessible by many users at the same time and is always changed with every transaction, like an automated market maker or so, like Uniswap, then it's not for all transactions possible to do them locally, whereas there you would need to do network executions. Local execution gives you the privacy property. So in theory, you only send a proof of the transaction and no one knows what was happening, just that anything correct happened. And obviously the client, the hardware requirements are harder or higher for local execution, but I will show you later, like we will do a proof together on your local machines, and on a MacBook, it works quite well, even on my iPhone. And the cool thing about Miden here is that the fees are way lower, obviously, if you execute transactions locally. And that means that the more privately you use Miden, the cheaper it gets and the more it scales. And this is different to other systems like Aztec or so, or like the previous Aztec, where basically when you add privacy to Ethereum, then it gets more expensive. And in Miden, it gets cheaper and it scales better the more people use it privately. And oh yeah, let's look at an atomic swap, and then maybe it gets clearer. So basically, when we the account interface could look like this, that Alice has a function, a public function, open receive asset and send asset. And then Alice creates a node. The node contains 100 ETH. And there is a node script. So a node always consists of the vault where the assets are stored, or the asset is stored. And the script, basically, that means whenever you want to have this asset, then you need to execute the script. And in that case, she says, okay, this account, in that case, Bob, or whoever wants to take it, receives the 100 ETH in his account, but needs to send 1,000 DAI to Alice. And Bob sees this node and says like, okay, well, I'm going to do that. And then basically Bob creates a second transaction. And in this transaction, he consumes Alice nodes, and it's in the same transaction, he needs to produce another node because of the script. And this other node or second node looks like this, that he needs to send 1,000 DAI and has another script in there and says, yeah, Alice can consume this, these DAI. And in a third transaction, then Alice consumes that and the swap is basically executed. And like this, all of this can be done in local transactions and privately. And in theory, Bob would not even know that it comes from Alice. In a more complex setting, if two accounts wants to swap on Uniswap, for example, and want to do a trade there, then both could send a node in a transaction, and this can be done locally and independently, and both would send to Uniswap, hey, I want to swap X for Y. And then Uni would wait for a period of time and consume all incoming nodes together and produce, like sequence them as well. This is important for MEV, and then produce nodes to send them back to the receivers. And in transaction 4 and 5, account 1 and 2 could then again locally consume their assets. But the important is that this transaction 3 cannot be done locally. So this is what we call shared state. Yeah. And this was about the transaction model. Should we do some questions, or should I go how we bundle all the transactions into?
I think this is probably a good time. So I know there are two very high level questions, which I think we should leave to the end, about comparisons with Zero and the ZK EVM Hermes. But let's try and, so there's, I'm just thinking that, say, for instance, in the simple example, there was transaction 1, 2, and 3. And so if, I guess if transaction 1 happens, then and then Bob does nothing, Alice can probably do some cancel or something to essentially get her transaction 1 back. I guess there's
Yes.
that. And then if Bob does transaction 2, then it's in Alice's best interest. And so Alice can't withdraw transaction 1 anymore. And I guess, can Bob withdraw transaction 2 at that time, or I guess he's locked in?
Yes, like as long as Bob's Bob's node is not being consumed, in theory, he okay, in this case, he cannot consume that back, because in the script, like in Bob's node, it says only, in this pseudo script, he could, in theory, he could also be the account, and then he could get it back. And normally in Alice script, there should be that the receiver, here it is, the receiver is Alice, so only Alice could consume Bob's node. But that depends, like your question is, yeah, it depends how you basically write the node script. So if Bob creates this node and has in his script also, I don't know, after 5 blocks, I can consume it back, then he can consume it back. So there's nothing protocol-wise that prevents him from doing so if it's in the script. But as long as the node is not consumed, someone can consume it.
How could Alice make sure that Bob set his script up so that she was the only one who could consume in transaction 3? Because obviously she doesn't want to have it that Bob consumes her 100 ETH and so gets the 100 ETH and somehow or other never has to give back or does something, but then quickly takes back the 1,000 DAI.
Yes, that would be super bad, especially for an atomic swap. So what Alice could do is she could say in her script, I don't know if you see my mouse pointer, but in her script, she can say, whoever receives this needs to create another node. And then she could basically, like all programs in Miden, can be expressed by hashes. And she could say, whoever consumes that needs to create a node with a script with the following hash. And so she could already pre-compile or hash the node that she expects back for the person who consumes that. And this hash basically includes only her as a receiver and no backdoor back from Bob.
That makes it a lot of sense. Yeah. All right. And then Bob either accepts that or he doesn't. And then so then transaction 2 happens, and then she will then be incentivized to do transaction 3 because otherwise she will never get her money. Yeah. Okay.
Exactly.
That makes a lot of sense. So I asked a question, but I'm sure there are other people. Ruud, do you have a question?
Yeah, I wanted to know, Dominik, if I were to look this transaction up on Miden Scan, just going off of like Etherscan, Miden Scan, and I were to observe, like, let's say these transactions were happening locally, what would I see and what would I not see within the transaction?
Yeah, that's a good question. Okay, let me answer that, and then we dive into how nodes are being tracked. But basically, we have state is being tracked in 3 databases. So we have an account database, which is the same as on Ethereum, and we have a node database. Like there are accounts and nodes, so obviously like they are equal entities. And the node database is in Miden Scan. Basically, you could look up, okay, is there a node? And then you would look up Bob's node. So every node has a hash. So if you know the node's hash, then you could look it up. And the thing is, if nodes can be stored privately or publicly. So there is an option if Bob wants to pay more or for whatever reason he wants to store a public node, then you would see exactly what you see here. So you would see the node, like the node hash, the node vault, how many assets and which assets are there, a script of the node. And 1 second, I need to look up the docs. Like the node has a serial number that you need. So it's a certain number, and the recipient and the sender. So this is the data you would see for a public node and some metadata probably. In a local transaction whatsoever, you would only see the node hash. So if you are not the receiver or the sender, then you would look up Miden scan, and you would only see, okay, there is a new node added to the nodes database, and it has the following hash. But you would not know what this node is about, who is the sender, what's the asset, or what's the script.
Would I be able to see transaction balances?
No, like it depends. So you have like you would see like if you know Alice's account and Bob's account, and you would watch them in parallel, you could not easily link the node to Alice and Bob if it's a private transaction. But you could, and then there is a nullifier database, which I will explain in 2 seconds, which defines which nodes are already consumed. So, but you need to know the node's data to link the nullifier to the node. So if it's a private node and you only know the hash, then you could see the whole nullifier database and would not know if this node is already being consumed or not.
And if a person who wrote the note included salt inside the note script so that, you know, maybe there was the additional comments, would that change the hash as well?
Yes.
Okay. So it could be,
yes.
Yeah, you could make it so that every transaction is completely private.
Exactly. But like you need to, like, there are different modes than you need to think of, but you somehow need to tell Bob. Bob needs to know some more data than the hash to be able to consume the node. So he needs to receive, because like node consumption means you can compute the nullifier, and the nullifier is being computed out of the hash of the data. In some entities, you need to know the salt. So if you want to consume the node, then you need to know the node's data, but this can also be in a other channel. Like I could send you data on WhatsApp or in an encrypted way, in any other way. So you can consume the node, but for others, the transaction graph would not be visible, who consumed the node and what's in the node.
Understood. Thank you.
Yeah. But maybe it makes more sense even if I explain how state is tracked in nodes. Yeah. So
that sounds good. Very good question, Rube. So that was very helpful. So thank you, Dominik, as well. Please go ahead.
So basically, yeah, like the state model means like now we have these accounts and nodes, and state basically means how all the accounts and nodes in which state they are and how they can progress. And so for a state model, basically we had these two options: the account-based state and the UTXO-based state. And the account-based state, as you all know, is very good for expressive smart contracts. There are some tries on UTXO-based models like Cardano and so to also have expressive smart contracts, but it's way harder, I would say. Account-based state is not great for concurrent transaction execution, and it's very bad for anonymity or privacy. And there are, again, like this is a bit blurry because also when you know block STM, for example, where they try to parallelize the EVM, but it's harder than on the UTXO based model. So UTXO basically is great for concurrent transaction execution. It's needed for privacy or anonymity, but it's not very great for expressive smart contracts. So basically, we ended up in our hybrid where we tried to get the both of best worlds, and the glue was zero knowledge. But let me explain. So basically, we also have an account database where we track accounts, either in the private mode, so only the account hash, or with the full data. Then we have a nodes database where we track which nodes ever were created, and a nullifier database, which tells us if a node was already being consumed. And these three databases basically progress from state n to state n+1 in a block. And this block contains the updated accounts, the created nodes, and the new nullifiers that were added to the nullifier database. And let me dive in. So the account database basically stores the current state of all accounts. It is sparse Merkle tree in our case. And for accounts with on-chain state or public state, the entire account state is stored. So we know which assets there are, what's in storage, what's the code. This is super important, obviously, for smart contracts. Like every account is always a smart contract, and the nonce. And but for off-chain accounts, we only see the hash. And the cool thing is, like with zero knowledge proofs, like the hash is sufficient again to verify a state transition. And yeah, like the nodes database basically stores all the nodes ever created. And this is an append-only accumulator, like in our case, a Merkle Mountain range. So you can always only add nodes to this, and this will help us with concurrency. And so even if most nodes are discarded, you can still add new nodes to this data structure. And yeah, this helps us with concurrency and to use it as a witness in a zero knowledge proof. And we have a nullifier database, which basically keeps track of all consumed nodes. So if you know the node's data and can compute the nullifier, then you can look it up in the nullifier database and see, can I still consume the node, and or the proof would fail if you cannot consume that node. And yeah, they are organized in epochs. So the nullifier database, the operator at least need to hold the full nullifier database to be able to create a new block. So this is basically our driver for state load. So that's why we try, at the moment, we think we can maybe prune it every 6 months or so. And then if a user wants to consume a transaction that is older than 6 months or 1 year, then he would need to be able to provide the Merkle path to it. But this is unclear how we do it. But in theory, if like we have, I don't know, 10,000 TPS or so, then it could become, this data structure could become quite big after 1 year, and then we need ways to somehow prune it. But yeah, like this is how we basically capture state in these 3 databases. And in the accounts and nodes database, you can always only have a hash or the full data, depending on what you want. And the operator can also decide to, I don't know, prune inactive accounts and maybe delete the data and only keep the hash to be able to manage the state requirements or the storage requirements. However, this also obviously has caveats. So if you if you only have a private account and you lose your data, then you will not be able to change the state of your account anymore, and no one can help you. And that means so this the data storage requirements or the data availability problem basically in Miden is being offloaded to the user. So you can still like encrypt everything and load it up to Google Cloud or so. But if you use Miden privately, then yeah, by its very nature, no one can help you if you lose your data. And yeah, this is how we track state. And this is also could be interesting. So how we hide the transaction graph, so or why we have nodes and nullifier database. Basically, when you have the first transaction, when the account creates the node, and then a new record is being put into the nodes database. And in the second transaction, account 2 would tell the operator, please add the following nullifier. But if the thing is, if you only know the node hash, then you cannot link the nullifier to the node hash. And this means that only, like it depends on which level, but it might mean that only account 1 and account 2 know who transacted. And you could, in Miden, you could even hide that. So only account 2 would only know that it consumed a correct node, but would not know from whom it comes. Yeah, and like these like this state model and the transaction model with always these like private or on-chain data, off-chain data, and network execution and local execution gives us 4 transaction modes in Miden, which is quite unique. And basically, when you have a network transaction and on-chain data, this is the same as on an Ethereum blockchain or on the ZK EVM. This is what we call a public transaction. Could also have stateless transactions, so off-chain data, but still network execution and proof. This is how we envision our first testnet. This is also super helpful for debugging. Obviously, when we would start in full privacy mode, it will be hard to debug. But these are then stateless transactions. If you have off-chain data and local execution proofs, this will be by far the cheapest way to interact on Miden. Then basically you can also have on-chain data and local execution, which, yeah, I don't know use case for that, but it's maybe for logical completeness. Yeah, and now I wanted to, this is easier to do it 1 second. I wanted to show you how quick we can do these proofs. Like the whole point, and maybe this also is the question that was in the chat before, like what's the difference to the ZK EVM? So it's local execution and proof. So in the ZK EVM, you cannot locally execute and prove and send only the proof to the network. This is the core USP, I would say, from Miden. And this is because the virtual machine for Miden, the Miden VM, is optimized for stacks. So, and it doesn't go the EVM route, basically. So, whereas the ZK EVM might be optimized for usability, so you can use Solidity or like even on an opcode level, it mimics Ethereum. The Miden VM is optimized for stack proofs. And that's why it's like, it's also way harder to use. So we had to invent our own assembly language, how to interact with this VM, but it's very fast. And because it's so fast, people can use it in their mobile phone, for example, or on their normal computers to create these proofs. And I want to, like in the chat, I sent you our playground. Like at the moment, we cannot create a transaction yet, I think end of the month, but I can show you the playground. I think you're seeing my screen still, right? Do you see the? Yes, okay, perfect.
Yeah, we can see it.
Then cool, you can also open it. But this is basically the Miden VM running in a browser. So Miden VM is written in Rust, and you can compile it to Wasm, which is quite nice. 1 second. To close all these windows. And this is basically how you can the Miden VM, and we will build the Miden client, or we at the moment building the Miden client around this virtual machine. So every client or wallet in Miden will run this virtual machine as well. And at the moment, this is how you need to code. Basically, here we have an assembly-like language, Miden assembly, and here it adds 2 numbers together. It has an input, like this is the witness or the secret input, and this is basically the public input to the VM. And just to show you this, like we can run it, and it gives me 3, meaning that 1 + 2 is 3. Okay, not very complicated, but I can also prove it. And now, like I'm also in a video call, but in 400 milliseconds, I got a proof that the Miden VM computed 1 + 2 and got the result 3. Like this is my proof. It's a stack proof, so it's not very, it's very big and might not be super useful. But you can also, prove more complex programs. So here, for example, I have the game of life, and it is 1,000 lines of Miden assembly code. But I can also prove it, but I'm not sure if it would work now in a video call, because this would be more resource intensive. Let's try. But it might take maybe 30 seconds or so, and then you have the proof. And no, okay, it was in 12 seconds. So yeah, like this, okay, it's a bit hard to read, and this is the main problem, I would say, of Miden. Like, it's hard to use, but it's very efficient. So basically, this is your universe of game of life at the beginning, and this is the end universe. Basically, this cell here switched from 0 to 1. Yeah, and then you have again the proof. You can verify it here. It verifies very quickly, and this is why it's like to create a proof, right? So probably you all know that, but to create a zero-knowledge proof is resource intense, but verification grows logarithmically. So it's very easy to. So that's why it's so much cheaper if users create their own proofs and then the network only verifies. So you can get high speed improvements, and as you can see, like verify this quite quickly. And if you would allow me to cheat now, so if I would say, okay, I have another result and I try to cheat it, then it should fail. Yeah. So yeah, and yeah, this is the Miden VM basically that runs in a browser. And with this, we are currently building our wallet and our client to be able to do this local execution. And if you want, we can look at a program more in depth, or maybe I first answer some questions, or whatever you want to, like, I'm open to.
Yeah, so I know I'm looking at that and thinking, oh, you're not going to get too many people developing complex things in that, but obviously the goal is to make it more simple over time. And where are you up to with that, and how far away do you think it is to have a higher level language and higher level functionality?
Yes, yeah, like I think, no, as you said, not many people will do it. We have some brave pioneers that already create stuff in Miden assembly. So we are working closely together with Mistin Labs from the SUI network, and they developed Move, right? Or not, but they use Move, and some of the team developed Move, and Move will be our first language, and we hope to have this in September. To have a compiler from Move to Miden assembly. And then we also try at the same time, but it might come a bit later, a subset of Rust to be able to code in Miden assembly then. And hopefully further back the route, we will get a Solidity as well. But yeah, so we don't expect people to code in Miden assembly basically. But yeah, in September, hopefully Move. And then let's see. I personally did try a little bit to code and Move. But yeah, it's a bit less tooling, I would say, than on Solidity, but it's also a fun programming language. And it has some cool new paradigms, how to treat assets. And they designed it with the paradigm in mind that, like, or at least some of their famous hacks on Ethereum would not be possible on Move. But yeah, let's see.
Yeah, that sounds interesting, and also it's not like you're talking 2025. You're talking sometime in, say, 4 or 5 months, maybe something like that.
Yes,
which sounds quite reasonable. Yeah, and so how confident are you with that 10,000 transactions a second? Do you think that's really possible, or is that?
Well, like, yeah, that's a very good question actually, and we discussed this in the team as well. So, in theory, yes, but like from the model, right? So if you like the concurrency that we have is like would really help. However, there are also synchronization points, obviously. So there is an operator, like if you would imagine a centralized rollup with only one operator, then you would it would be easier. So when we stay at this model, but still the centralized operator needs to update the databases sequentially and needs to create block proofs at the end. And at the moment, our prover would not be fast enough for 10,000 transactions. So I like the Miden VM, because this is then at the end, and in our case, the prover is the bottleneck. But like at the moment, it only runs on CPUs. and we might get up to 100 or 10 to 100 TPS, depending on also which hash function we use, and so for recursive verification. So, or to give you some numbers, we aim for recursive verification with to 2 to the power of 16 cycles, and that, yeah, will give us maybe 10 TPS or so when we only run it on a CPU. You could parallelize that as well, but we are working together with the team that works on GPU acceleration, and that will give us a speed up. And then we are thinking of maybe FPGAs or so, or some hardware design that helps to increase the speed. So from the state model and transaction model, it is possible, but the question is how quick you can do recursive verification, but you can parallelize a lot of these things. So yeah, we are confident, but it's always like, I would love to prove it first before to do a huge marketing campaign with it, so to speak.
Yeah, look, I fully understand that. And I'm sure as we go from May towards September, the numbers will become far more firmer. And
yes,
yeah, that'll be good.
Yes.
All right.
But at least, or maybe to add one sentence to that, is the problem that these high performant blockchains like Solana or even BSC or so had, that is what we prevent with Miden from the design, like that the state explodes and that it grows too big, that it cannot be handled anymore. And this is because with zero knowledge proofs, you only need part of the state or like to be able to produce new blocks. But with our state model and obviously knowledge proofs. But yeah, so let's hope.
Sounds good. So at this point, does anyone have any more questions, or so shall we go on? So you've got more slides, don't you, Dominik?
Yeah, but like it's also but these are only for applications. I can show you maybe one thing that could be interesting because it's also novel. Is basically our updatable transactions, because you have these nodes. Like, okay, so we think it could be a good use case, and at the moment we are just collecting feedback actually from companies for on-chain order book exchanges. Could be possible with Miden because you have this high throughput and you can update your transactions. So you could have things like FTX or Kraken really on-chain, which could add more security and more credibility. And complex, incomplete information games could be super interesting on Miden because you have this zero knowledge proving with the user, which could hide moves and even in a large scale. But yeah, I want to show you how an order book would work, which is quite interesting. So when you think of like a market maker or someone who creates a node with 100 ETH, and he has a node script, and he only shows the hash of this node script, like the root. Our programs are always like constructed in Merkle trees. But then you would see the node hash, and this would be on the order book, and then he reveals one leaf of this and says, whoever wants these 100 ETH, he needs to send me 1,000 DAI, when you remember the example from before. This is our first order. And then after 1 second or 10 seconds, he sees no one takes this order, then he can reveal a second leaf and say, okay, whoever wants these 100 ETH, he sends me 500 DAI. And this update, because the node is already in the nodes database, doesn't need to be an on-chain interaction. So he can just reveal another leaf basically on any platform. And this could be in no time. And then people can already consume the node using the second leaf. But if no one takes, then he can just recall it and take back his node. And that means that you only create one node at the beginning, and then you can always update it. Okay, in this time, like if you use a Merkle tree, you cannot continuously update it, but in a discrete way. So you have maybe however big your Merkle tree is. Maybe you can store 1,000 different orders in one tree. And yeah, with incomplete information, games could also be funny. Like this could be a game. Alice moves something and you only see the hash, and Bob's has a move and Charlie has a move. And then the network would say, okay, all moves are correct. And then you would only see that Alice gets 1 ETH and the rest only 0 ETH, like in the return node. So Alice seems to have won, but you don't know which game it was or what they did or what their move was. And yeah, but this is just a stupid example, but you can obviously build more complex on-chain multiplayer games or whatever, yeah. And this is our roadmap basically. So in July, we want that Alice is able to send something to Bob in our 4 transaction modes. So it's our first testnet, but a very limited dev testnet. And October, when we have our move compiler, we want that developers have a fairly good experience in our public testnet and hopefully have some proof of concepts that show how fast Miden could be or how private. So maybe to have one cool game and cool DeFi application. We have it then end of the year on our testnet, and then mainnet we approach end of Q1 next year. But that's it. And now back to you, Peter, to the merch store.
Yeah. I'll tell people about this. So for those people who don't know, the merch store is now live, and so you can either get to it from the YouTube channel by going into the store, click on store, or you can just go to that link. So Ethereum Engineering Group -shop.forthwall.com. And when I get to it, I will actually put this in the meetup.com description so people know about it. There are a whole stack of different t-shirts. The manufacturing is theoretically global. So hopefully the actual cost of delivery shouldn't be that bad. They've done it at cost, so it should be, and there are lots of interesting shirts. All right, yeah, next slide, please. So there are a stack of talks coming up, and this one's been great, and the next one on how do contract auditors actually do their, what's the process, is coming towards us, and that'll be really interesting. You've got Max Oliver from Zelic, who've done tons of audits. You've got Sriram from Eigenlayer. So he, I think, is the founder of Eigenlayer. So that should be super interesting as well. And he's going to talk about how Eigenlayer works. I'm going to be then talking about AI and what are my findings from using a whole stack of different types of AI, how good it is at finding bugs in code. And yeah, so that'll be me trying to do some very fair analysis. And David and then Philip are going to talk about cross-chain and issues with that. And the next slide again, please. Okay, and so if you're watching this on YouTube, you can join the meetup. If you're here live, you can watch recordings of previous talks and this talk on YouTube. There's also a formal methods reading group. And yeah, I think that's about all there is to it. So look, thank you, Dominik. Are there any more questions for you before we call it a day? Because it's been such a big subject that surely there's a lot of things to be considered.
There might also be, 1 second, I can send you, like we have a blog post where we try to summarize it.
Yeah.
And maybe if you want to give feedback, then you can read it and just send me your thoughts.
Sounds good. I mean, look, I think even the whole idea of this actor-based model in a blockchain is a really interesting idea, all just by itself. Yeah, sort of gets you thinking. And I know for Sandra, who's also in Europe at the moment, I'm sure she's probably going, I need another coffee, or maybe you don't. I mean, Sandra's super smart, so she can handle anything at any time of day or night. I don't know, what do you think, Sandra? Actor-based model, is it better than account and better than the TXO? Or UTXO?
Oh, that's a tricky question to answer, Peter. I'll yeah,
Yeah.
I think time will tell.
Yeah, well, I guess a different model, and maybe different models for different use cases.
Yeah, yeah, for sure.
All right, are there any last questions for Dominik before we call it a day? All
Then
right.
thank you a lot.
Look, thank you very much for your talk. That was really good, and have a great day. And everyone, for those who can make it, see you in a week for the next talk. Bye-bye.
Thanks for having me. Bye.
Bye. Bye.
Bye.